Last time we were looking at the idea of hash codes and using the get hashcode method that's available in .NET. And I thought this time we'd look at a completely different use of hash codes, which is in the field of password encryption. And the reason I'm doing this is really twofold. One is just that it's interesting to know about in its own right, but also to emphasize the fact that just the concept of hash codes is something that can be used in lots and lots of different situations, and that there are different things you've got to concern yourself with depending on those circumstances. And so what we're looking at here is this idea of password encryption. Now, when we're dealing with encryption in general, there's actually three basic forms of encryption that we have. We have what is known as symmetric encryption, which is where the key that we use to encrypt the data is exactly the same as the key that we use to decrypt the data. And that form of encryption is useful when we're storing data locally, so on a hard drive, in a file, or in a database, something like that. The next type of encryption we have is what's known as asymmetric, and there the asymmetric feature is that the key we use to encrypt is different from the key we use to decrypt, and so the person who's encrypted the data can't necessarily decrypt it if they don't have that other key. And that is used whenever we want to communicate data across a network or anything like that. And then the third type of encryption, which we're going to look at here, is what is known as one-way encryption. And with that, we have an encryption key, but we have no decryption key whatsoever. So that's a bit like having write-only memory. We can convert our data into an encrypted form, but it's impossible mathematically to decrypt that to get it back to the original. And that may seem like a very odd thing to do, but that is the basis of password encryption. Now, if we've got a website, all three of these forms of encryption may well be available. We'll be using asymmetric encryption for the communication between the browser and the server. And that's the basis of HTTPS, of Secure Sockets Layer. That's how that's done. We'll also maybe be using symmetric encryption on the server itself. So any data we're storing in the database that is sensitive in any way, for example, credit card numbers, something like that, those should be encrypted just in case if anyone managed to get hold of the database file and steal that, that's useless to them unless they've also got the key. But that is still a risk, because if somebody steals both, they will have access to the data, or indeed, if you have a rogue employee who gets hold of the password and the database, they could start doing mischief by getting at that data. And so that's why, when appropriate, we use this idea of one-way encryption so that nobody can ever decrypt the data once it's been encrypted. And that's typically used for actually encrypting passwords. Now, it may seem like a very odd thing, but it's really quite simple. The point is, if a user registers, enters their password, that then goes through this one-way encryption process to produce an encrypted form. When they then log in, we don't need to decrypt that encrypted form. We simply need to take the password that they've logged in with, put it through exactly the same encryption process, and if the encrypted form of what they've entered matches the encrypted form of what we've stored, then clearly they've entered the correct password. And so that means that without ever storing the password itself, we can still have the security. Now, something I'm sure you've done, I've done it loads, is forget my password on a particular website. And they'll normally have a button to press, you click on the button, and it sends you an email. Now, years ago, and occasionally today, that email will contain the password that you'd forgotten. And you'll think, oh yes, that's what it is, and you'll go and use it. Now, that may have been forgivable a few decades ago, but if you see that today, that is really bad security, because that means that this organisation has stored your password in a retrievable way. They may have encrypted it, but it's clearly not one-way encryption because they've also managed to decrypt it to send it to you. What you should be seeing universally these days is that the email they send you when you've forgotten your password simply gives you a link to reset your password. They can't tell you what your password is because they don't know it themselves. And the algorithm that's used to do this one-way encryption is actually a hashing algorithm, but it's not the one that we use with the get hash code in C#, because remember that only gives us back a 32-bit integer. Far too few possibilities there for it to be secure. So what's typically used, there are other options as well, but what's typically used is an algorithm known as SHA-256. SHA stands for Secure Hash Algorithm, and 256 actually means that the hashed version we get is 256 bits. And it's a standard algorithm, widely available, and it's implemented in .NET and all sorts of other libraries as well. So let's take a look at how we might use that. So what I've done here is I've got this user record, and at the moment a user simply has a username and this thing we've called a password hash. And then in my program, rather than actually using a database, but that's what you'd use in the real world, I've just got this dictionary that we're going to use the username as a key and then this user object as the value we put in there. And then the program as it stands simply has a loop until we quit, asks us whether we want to register or log in, and then based on that, we will either create a new user by entering the username and the password, or we will try to look up an existing user. But at the moment, there's no password checking at all. So if I just run that up, and if I go to R for register, and then if I put in a username of Fred, password, as I say, doesn't matter at all at this stage. We can see it's just recorded that it's registered Fred and Pebbles. And then if I do a login, and if I try and log in as Fred, doesn't matter what the password is, it still finds Fred. Whereas if I try and log in for, say, Wilma, again, doesn't matter what the password is because we haven't got a Wilma there at all. So let's introduce some password hashes into that. So what I need to do is put in another method here that is going to be a static string hash password, and it's going to take the password as a string and return the hash version. And to do this, we use the class from the .NET library that gives us this SHA-256 algorithm. So I'm just going to say var SHA equals, and then we can say SHA-256, just get hold of the namespace. So system.security.cryptography, obviously enough, and then create, and that will create us the object to do this. And if we take a look at that, we can see that it's got a method called compute hash. So that's what we're going to use. We can also see it's got a dispose, which reminds me, I should have said using on there. And then if we look at that compute hash, you can see that what it actually takes and returns are arrays of bytes. So although we're going to do this on a string, actually the algorithm works just on numerical data, arrays of bytes. That's easy enough because we can convert that. So we can say var as bytes equals, and then we can just say encoding, again get a namespace, and then just default, and then get bytes, and so that will convert our password as a string just into an array of bytes. So nothing special there. And then we can say var hashed equals SHA dot compute hash, and then we can just pass in our as bytes. So that is the actual hashing process. But what that returns is an array of bytes, which although you could store that, is a bit inconvenient. So what's normally done is we then take that, but what we return is that converted to a string using what's known as base 64 encoding. So if we do a to base 64 string, pass in the array of bytes, and that will give us back our string. And base 64 is simply a mechanism where we take, rather than having data as binary or have it as, say, hexadecimal, we actually have it as base 64. So it uses 26 lowercase letters, 26 uppercase letters, 10 digits, so that gives us 62, and then the plus symbol and the slash symbol, that gives us 64 different characters. It's just a relatively compact way of storing data as a string. But bear in mind, it is not encryption. It's simply a form of coding. It's completely reversible. There's no security there at all. But that's what we've done there. And so what we can now do is on our register, having got hold of this info, which contains the username and the password, we then want to hash that password. So all we'll say is var hashed pw equals, and then we'll do this hash password and pass in info dot password. So that will give us the hashed form, and then we will pass that in there. So we'll also say password hash equals hashed PW. And then also this console write line, let's just move it down a bit, and as well as putting in the username and the password, we'll also print out the hashed password. So that's going to be hashed PW, and you can see why it's convenient to have it as a string. So if we run that up now, and we register, and we'll put in Fred and Pebbles, and then you can see that is the hashed version containing lowercase, uppercase, digits, slash. There's no actual pluses there. There's also, I didn't mention an equals. That's just used as a padding character in case the data you have doesn't exactly align with the number of bytes you've got available here. But that is the hashed password. And although we could translate that back into bits, because the base 64 is not an encryption, we could not then translate those bits back into the password Pebbles. It would be mathematically impossible. So let's also now put that on the lookup. So on our login, we're going to do exactly the same thing. So we're going to take that bit of code to hash the password, and then here we'll put it in here. We'll again make sure that it's printed out just so we can see what's going on. And then what we're going to do is just check to see whether that matches up. Bear in mind, if we didn't find this user at all, it could be null, so let's just put a check in for that. But then we'll compare the password hash that we recorded with the password hash that was entered. And if it matches, that's fine. If not, we'll just say no one. And in fact, because we now know it must be a valid user, we don't need to muck around with that sort of thing, so we could just tidy that up a bit. So now, if I enter that, let's again register Fred and Pebbles, and then if we log in as Fred and Pebbles, then we can see that the hash of what I entered is the same as the hash of what I recorded, and so that finds the user. Whereas if I tried to log in as Fred but with a different password, then we can see you get completely different hash code. Doesn't match, so we haven't logged in correctly. But all the while, we've never actually stored the password, only the password hash. So if our database were stolen, looked into, no one would know what the passwords are. And that has huge benefits because it means not only are we helping to secure our own site, if any of our users have reused their passwords over multiple sites, which they shouldn't do, but people do, then if you could steal their password on one site, you'd be able to use it on another. But here, because it's hashed, you can't see those passwords at all. Worth emphasizing a couple of the differences here between this SHA-256 hashing and the simple get hash code we had when we were looking at those features in .NET. One obvious one is the size of it, much, much bigger, 256 bits. Another one really important to point out is, remember we said with the .NET get hash code, there's no guarantee that you'll get the same hash code for the same object on different runs of the program. And that was fine the way we were using that, but where we're using this, it has to be exactly the same because we are storing these hashes. So again, it's still hashing, but different use and therefore different details of what's going on. And another difference is the get hash code that we had in .NET and C# wants to be very, very quick to calculate because it's not there for security, it's just there to improve performance like we had with the dictionary and that sort of thing, and so that wants to be quick. The SHA-256 algorithm is deliberately slow. Now it's not horribly slow, we didn't notice any delay here, but it is quite slow, and the reason for that is if anybody wanted to do a brute force attack, so just to try guessing password after password after password until they hit the right one that produced the appropriate hash, the fact that the hash algorithm is relatively slow makes that much harder. And it's the algorithm itself that is deliberately slow. It's not the implementation, because anyone can write their own implementation. The algorithm is publicly available. The algorithm itself is deliberately designed to be slow. Now, we've still got a problem here, though, which is if we have two different users. So let me register another user, and this one is Wilma. But Wilma's password is going to be the same as Fred's. Okay, and so if we do that, that obviously means that Wilma's hashed password is going to be the same as Fred's. So we saw that one is Fred's up there. Wilma, completely different identity, but has the same password and therefore has the same hash password. Now, you certainly don't want to try and prevent people from having the same password, because that actually would be a vulnerability. If you log in and you're told this password has already been used, then you know that's a password you might try on somebody else. So you certainly don't want to do that. But the problem with this is twofold. One is, if someone did steal our database, they could notice that both Fred and Wilma have the same hashed password, and then with a bit of research they could find out what Fred and Wilma have in common, discover they've both got a daughter called Pebbles, and guess that that's what the password might be. The other problem with this is, it does mean that this approach is vulnerable to what is known as a dictionary attack. The basic idea of a dictionary attack is you take a dictionary and you just go through all the words in it, put them through the SHA-256 hash algorithm, and you get the hash for each and every word. Now that's going to take a long time to do, but once you've done that, that will be able to break into any site that uses SHA-256. One way that people try to offset that risk is a way that's recommended to have your passwords is to use two unrelated words, stick them together, that is going to be your password, like unctuous turntable, something like that. That's still vulnerable to this dictionary attack. It's just rather harder because the dictionary attack has to not just go through the dictionary once, it's basically got to go through the square of the dictionary to do every combination. And then if that's no good, you can have a combination 3 and so forth. But the point is that once you've got this dictionary, because it's reusable across sites, it can also be sold. So any particular hacker doesn't have to go through that dictionary attack again. They don't have to produce their own dictionary. They just have to pay for one, and then they may be able to get into a website. So the way that that is obviated is to use what is known as password salting. And the way we do that is like this. What we do is when the user registers, we produce an extra bit of information known as a salt. And all that needs to be is typically a random number or maybe a GUID or something like that. I'll do it as a random number. So what I'm going to do is say random, rand, new, and then I'm going to say int salt equals rand dot next. So that is simply going to give me the next random integer in the full possible range of integers. So that's going to be 32 bits, 2 to the 32 different possibilities. Should be big enough, but if you want greater security, you can have an even bigger salt. What we then do is we have what is known as a salted password. So we say string salted pw equals, and then all we do is stick those together using some kind of string concatenation. So I'm simply going to say here, we're going to have the actual password, so that's info.password, and straight on the end of that, we're going to put the salt. Let's just print that out so we can see what's going on. And then when we do that, that means we now hash the salted password. So not the original password, the salted password. And then what we also need to do is record that salt. So if we just go to the user, let's just put in another, in this case, int of salt, and then just put another parameter on there. And then we also store the salt along with everything else. So salt equals salt. And what that means is now if I register two users, so let's register Fred with Pebbles as the password, and then we can see that's Pebbles 3321811161, so that's password plus salt. And then if I register Wilma, and if Wilma chooses the same password, we've got a very good likelihood that it's going to be a different salt, and therefore, because we're then hashing the salted password, we get a completely different hash. And so that now means that you can't spot that these two are the same password, even though they are. And if you now wanted to do a dictionary attack, you would have to have 4 billion different dictionaries, because you'd have to be doing it for all the words followed by a salt of 1, all the words followed by a salt of 2, up to all the possible values of an int. So that would become not impossible, but just extremely difficult to do in, the lifetime of the universe. Then the next thing we've got to do in order to then log in is we've got to make sure that, again, on the login, we don't hash the password, we hash the salted password. So that means I'm going to actually have to firstly get my user, and then remember that user object does have the salt stored in it. And the salt doesn't need to be secret, the salt just needs to be there. So now we're again going to merge them together in exactly the same way. In this case, not the generated salt, but the stored salt. And so that will now mean that if I register Fred with Pebbles and then I log in as Fred, I don't need to type in Pebbles 868, etc. I don't need to know the salt at all. I just type that in, and then that works okay because it fetches out the salt, sticks it on the end of Pebbles, does the hash, and therefore the hashes match up. So that's the basic way we go about doing this one-way encryption using the SHA-256 hash algorithm. Having said that, I've done that for explanation, but you should never do this sort of thing for yourself, because there may be mistakes that you make, latest hacks that have been realised that I'm not aware of, or just the fact of plain bad programming. There may be security loopholes in what I've written there. Whereas if we use one of the built-in classes to do the whole of this, it'll save us the effort of typing all of that, and also it will have less chance of security risks. So although that's interesting, I think it's worth knowing what's going on, I wouldn't do that for real. What I would do for real is just let the system get on with it. So what I'm going to do here is actually add to this project a new website. So let's go for an ASP.NET Core web application, just call this web. And then the thing I've got to remember to do here is make sure we give it some authentication. So just go for the basics of individual user accounts and then create that. And then the first thing we can look at is if we go to just say the home controller, if we still wanted to do the hashing for ourselves but not write that low-level code, there is actually an injectable object. So if we inject for I password hasher, and that's a generic, so we put in there identity user or whatever our user may be, and just call that hasher, and then we're going to need to get hold of the namespace for that. But on that hasher object, we have a method called hashPassword and a verify hash password that are doing pretty much the same as I was just showing in the console application, but I haven't had to waste time writing it for myself, and therefore there is much less risk of a mistake because I haven't really understood all the possible things that can go on when hackers try to get into this. But even then, we don't actually need to use that because for the most part, that is all handled for us at an even higher level. So what I will do here is, we'll notice we've got in app settings, it's already set up the database connection for where it's going to store any of our data, but in this case it's going to store the login data. I'm just going to remove that unique ID just to make it a bit easier to read. If I just do an update database, then that will create, if we look in here and just do a refresh, that database. And if we look in there, you can see it's got all sorts of tables. But the main one we're interested in is going to be that ASP.NET users, because if I take a look in there, although we haven't got any users as yet, we can see we do have a column as well as the username. We've got that password hash in there. So if I now run this up and then register, so I'll register as Fred at bedrock.com, and then the password I'm going to use is PA$W0RD. By default, there's a certain level of password security that you need to have, non-numeric characters and that sort of thing, and it turns out that PA$W0RD just fulfills the requirements, but I would never use that, obviously, as a real password, but it's useful for these sorts of tests. If we then register that, that'll take us in there. In reality, we should also have two-phase confirmation, but I'm just going to bypass that because that's not what we're talking about here. So that's confirmed, and if we now go back and rerun that query, then you can see that there we've got the password hash, and we can see, obviously it's encrypted, but it's that base 64, the same sort of thing we saw earlier on. If I then register for a second time, so let's re-register, this time as Wilmer at bedrock.com, and use the same password, $PA$W0RD, and go through there, and then go back in here, and we'll see, as we'd expected, that they have different hashed passwords. And that's done because there is salting. Now, something that changed a few versions back of this, there used to be a separate column in here which was used to store the password salt, similar to the way that in the program over here, I'd just put in a separate field for that salt. But the way it's done now actually is slightly different. If we just run this one up again and just do a register, you'll notice that actually that what we've got in here as our hashed salted password is rather shorter than what we've got in here under that password hash. And that's because, and it's kind of a clue because all of that data at the beginning is very similar, that password hash does not actually just contain the hashed password, it also contains lots of other bits of pieces of information as well, one of which includes the salt in an unencrypted form. So rather than have separate columns, they've just decided to bung them all together into one big chunk of data and put in the same column. But exactly the same thing's working. When we log in, it decomposes that, takes out the salt, combines that with the password I've entered, hashes it, and checks it against the hash. So that is how we do password hashing. That's a really good feature to have in terms of security. I think it's interesting to understand, but we can see certainly with an ASP.NET website, the actual work is done for you just by clicking the appropriate box. And that is always the best way to do it, not only because it's less effort for you, but also because any security weaknesses that you might have introduced by not understanding it, you'd hope that would be solved by using these standard versions. So another way of using hashing, hope you enjoyed that. If you enjoyed it, do click on the like button and do subscribe, and I'll see you next time.